I showed you so this the geometry of the shaft is given, and we can see that and we have the two bearing systems. One is on the left end, another one is on the right end, and in between, and we have two steps, right? So see these two steps. So these two steps and the cross-sectional area is different from one another, from each other. And also on the left end, on the left side of this beam, there is 18 pound force, which is a concentrated force. And on the right side of the beam, there is 32 the pound force. And in order to highlight on these two locations that we apply this is a two concentrated force on, I'm going to show you how I'm going to model. Okay, so on the bearing system, and we for these two bearing systems, and we only take care of the center of the bearing system, of the center of the left bearing system and the center of the right bearing system. Now I'm going to show you. I'm going to build a model. Okay, so first, build a parts here and double click parts and build a model. The parts here, and so we say, you can just say, let's say natural frequency. Right? Natural, this is frequency. Is frequency. We solve this frequency first, and this is a 3D and deformable. Now we are going to use the where. So use the where, and then we apply these profiles. I'm going to show you how to do that. So this is one way. Another way is that, and you build this is a 3D extrusion model, and that one is not. It is working, but I prefer to use this where, and then we prefer and to use to apply this is the different profiles on it. So I'm going to show you. And here, a 3D deformable where, and so this is an approximate the base feature we use. This is a 3D deformable. We don't use shell, and we don't use we use where. Okay, where, and this is a planar. So this is the approximate size, and we use because from the center of the left bearing system and to the center of the right bearing system is 16 inches. So we can just use let's say 30 inch for this is for this board will be good enough. That's 30. Right? So this is the interface, and we can draw it. Now, we are going to draw, use this tool, create lines, and this horizontal line, right? So horizontal line from here, and to draw this one, and we use this one, and to stand for the line from the center of left bearing system, and to the left shoulder of this shaft, of this is between these two bearing systems. So this is our first segment. And then we draw another segment. This segment and stands for from the left shoulder of the left shoulder of the left step and to the location where we apply the 18-pound force. So this is the second segment. The third segment is from the location where we applied 18-pound force and to the right end of the first step also, which is the left shoulder of the right. This is the step, right? So the same thing. Go here, and then from here and to the location where we apply the 32-pound force. So this is that segment. And then from the location where we apply the 32-pound force onto the right shoulder of the right step, we have this segment. And then from the right shoulder of right step and to the center of the right bearing system, and we have this segment. Now we have finished. Then we press the ESC escape, right? And now we can just dimension all these segments. So we dimension, use this tool, dimension. So here, for first one, and we know that this is the is 1 inch. Yes, 1. We just enter. And from the second segment is also 1 inch. We can see from the geometry of the beam, we know that this is 18-pound force is applied at the 2-inch location from the center of the left bearing system. So here, but here, if we dimension this one, and this one is 1, right? And then we enter. Also from the distance from the location where we apply 18-pound force and to the right end of this is left step, or the left shoulder of the right step is 9 minus 2 inch. So here is 9 minus 2 equals 7 inch. Then we enter. And then next segment is 14 minus 9, which equals 5 inch. Here is this light segment's length is 5 inch. And then the next segment is 1, 15 minus 14. And 15 and 14, they are measured from the center of the left bearing system. So we know that, and here is 1 inch. And here the left this segment, this very end segment, this one is also 1 inch. 16 minus 15 is 1 inch. Now, we have finished dimensioning all these light segments. Now we can press this one and to say we're done. Now this is the beam and we just created, right? And then we material and we need to specify the material, create the material, and be very, very careful. Because I told you several times, the Abaqus does not have its own units. And so we need to be very careful when we use the units, and we need to be consistent. And now we use these inches, the basic unit, inches, inch. The force is pound force. And then the Young's modulus I give you is 209 gigapascal. And gigapascal is an international unit. So we cannot use it here. If we use it here, and so this is, and your answer will be totally off from what it is supposed to be, okay? Because we need to be very, very careful and be consistent. The Young's modulus and 209 gigapascal and equals, I'm going to show you. So because this is a natural frequency, this one is natural frequency, and for this one, and the density, okay, density, and the density rho equals 7,860 kilograms per cubic meters. So, but that one kg kilograms per cubic meters, that is the international unit. So this mass density must be converted to the English unit. The English unit is this one. Okay, so 7.3547 E minus 4 So the unit is pound-force multiplied by second square divided by inch the power 4. So this is the number, the density rho, and you should enter. The otherwise, and your answer will be totally off. The mechanical, elastic. So elastic Young's modulus, I give the value, the Young's modulus value I give you is 209 gigapascal. So this 209 gigapascal must be converted to the English unit. And for our case, and 209 gigapascal equals 3031288.18557 on PSI. So you must change, and this one from the gigapascal and to PSI. PSI is a standard unit. And Poisson's ratio is just a ratio, and this guy does not have any units, just put the Poisson's ratio. So this is our material, and we click OK. Now you can see one material has been created, and then we are going to create profile. Okay, so profile, and we know that, and this bearing system and these two bearing systems, they have the same profile. The same profile actually is a cross-sectional area. They have the same profile, and this is between these two bearing systems, we have two steps, right? So the left step, and they use the same profile. The right step, and they use the same, they use profile. Because on the left step, we have a concentrated force, just concentrated force for 18-pound force, and for the left side, next to the 18-pound force, and that's one leg segment. And for on the right side of 18-pound force is another segment. We just created two segments, and these two segments, they have the same cross-sectional area, and that's the reason. And these two segments should have the same profile. So same thing on the right step, and one is left to the 32-pound force, another one is right to the 32-pound force, and these two guys we created on two different leg segments. However, we know that these two guys have the same cross-sectional area, and that's the reason we need to apply the same profile to these two segments. So when we look at the geometry of this this beam, and we know that we should create three profiles, and each profile stands for one cross-sectional area. And one profile 1 is for this two bearing system, and profile 2 is for this is the left, for the left step, and profile 3 is for the right step between these two bearing system. Let's go. Let's create profiles. Profile, and this profile 1 and circular, and we know this is circular. Okay, and circular one, circular continue. So this dialog appears. You can see, and this dialog appears, and the parameter you ask to enter is the radius. However, the diameter for the different locations of this shaft is given. And be very careful. As I said, for profile 1, and we are going to apply profile 1 and to these two bearing systems. The two bearing systems diameter is 2 inch, and here it asks this is the radius. So this we need to put this 1.0 inch here. So this is our first profile. And similarly for the second profile, and also is a circular, and we continue. Now this time we use the radius of the left step between these two bearing systems, and the diameter is 2.472. Remember, here we need to enter the corresponding radius. So this is diameter divided by 2, and then we get the radius. The radius here equals 1.236. Okay? So then we click OK now. And then we create another profile, the third profile, profile 3, and which will be applied to the right step between these two barren systems. And now we click this one. So also scalar, continue. Now this time, remember this time it is the radius we need to enter instead of diameter. Diameter equals 2.763, and then radius equals 1.3815. 1.3815. And then click OK. Now we have created profiles here, and then we can create sections. The sections is related to materials. For our case, we use profiles. So the sections is related to both materials and profiles. So now we create sections. The section 1, and we use beam because we create a beam here. And what type of beam? We just use beam not truss. The beam here, section 1 is for these two barren system. Continue. Not barren system, I'm sorry, for the shaft part on the barren system. Continue. Now, this is a profile name, profile 1, and material 1, and section Poisson's ratio, we know 0.3. We put it here also. And then continue. Then do the same thing, we create the section 2, also beam, the type is beam, continue, and during analysis, I'm sorry, here's a profile 2, material 1, the same material, and 0.3, but this is a profile 2, and click OK. And the same thing, and to create the third section, also beam, type of beam, category beam, time beam, and continue. And so this is during analysis. This is a profile 3, and material 1, and 0.3. And then click OK. Now we have created 3 sections. The next step will be, and we assign the sections and to the corresponding segments. And we know now I'm going to assign. Go here, go pause here. Section assignments, double click this one. And then here this is the statement appears. And select the regions to be assigned a section. And I don't want to create a set here, so I toggle this off. Now I want to create this one, assign this one, right? Using the shift, and this one, I select these 2 segments that I'm going to assign. This is a profile 1 on. And then I click OK, done. And which section you want to assign this one? And section 1. And then I click this part, and also this part. And this is both of these light segments are on the left step between these two barren systems. For this one, I'm going to done. Right, click done. On which section? This section 2. And then I click this one and this one, and these 2 segments have the same profile. Done. Which one? Section 3. Now, okay, I have created all these sections from all these light segments. Right, then and don't forget, for profile, we need to assign beam orientation here. Click this one and say select a region to be assigned a beam section orientation. And select the box all these light segments and click done here. Now here, enter approximate N1 direction tangent vectors are shown. So this one is okay. So this is the 0, 0, negative 1.0. So this one is okay. And then click OK to confirm input and click OK. Right? And so we know that this is the in Y direction. In this is the Z direction, and this is the Y direction. So this is the beam's the direction. And then now we're done. And after we finish assigning these sections and also beam orientation, and next step will be we create assembly. Go here and double click these instances. So parts, and so independent, we select independent. And OK. Now you can see, and this the whole beam and turns the blue, right? And then next step, we create these steps. This natural frequency. Okay, this one is the model 1. We are going to create natural frequency. We select natural frequency. Just to remember, for natural frequency here, we use linear perturbation and click frequency here, and then continue. And then this dialog appears, and we still remember we use Lake zones. This is eigensolver, number of eigen values requested, and we want to use specify a value. Let's suppose we use 6 here, and minimum frequency, and we use 1, and the maximum frequency, and we use 1000, and toggle this off, and then click OK here. Now this step has been created. And then we go to boundary conditions. The double click boundary conditions. And so make sure this boundary condition is from initial step. We click this displacement and rotation and continue. And for this is a shaft. This shaft, we have this shaft is on the two sides. There are bearing systems that support this the two left end and right end of this shaft. And so for this one, we click done here, right? And so we want to constrain this point in 3 translational directions. And we don't want this guy to move in translate in U1, U2, U3. However, so this guy should be able to rotate along this is x-axis, y-axis, and z-axis. And this is boundary condition 1. And then double click it, and we click double condition 2. Boundary condition 2. Continue for this end. And we don't want this guy to move in the U2 and U3 direction, but we allow this guy to move in the X direction. Right? So and this guy can rotate in X, Y, Z about X, Y, Z axis. So we just constrain U2 and constrain U3 and relax all other 4 degrees of freedom, and then click OK. Now I have applied the boundary conditions, and because here we are going to do the natural frequency analysis first, so you don't need to apply any loads. The natural frequency is natural frequency. It is totally dependent upon the structure itself instead of any externally applied load. What is the next step? Next step will be meshing. We use this module and click this meshing here. So this is a tool. These tools appear to the left of this is a screen. And so first one is we seed it, and seed part instance. And so this is a global seed, and 0.7 is too huge, and we can just use the 0.0 0.01. So this is fine one. Okay, so this is my seeds. Click done. And second step is that, and second step is assign mesh control. Select the region. I will box the beam, and then done. Oh, no, what was wrong? Select the region, then done. Why? Just one second. Let me assign. Okay, mesh. Okay. So this is mesh, the seed we just specified, and then we go here, assign. So this one appears, and we can box everything here. And click done. Why it does not? And select region to assign element type, and we should select the beam. Right? Select the beam here. Click OK. Right. Assign mesh control. Why I did not allow me to assign mesh control there? Okay, let's see what will happen. They won't mesh it. Okay, to mesh, yes. So this is elements. Right, so you can just follow this procedure. Now, and so this is model 1, and I would like to let's see. We save it. Always save. So we call this one is a shorter model diamond. Okay, and always remember to change to save it. Now model 1, I want to change the name, rename it, and I will say natural frequency. Or model analysis. Right, so this natural frequency. Now I'm going to create a job. Job 1, I will say natural frequency. Now job 1, I call it natural frequency. Natural frequency, short. Continue. Done. Now I can run it now. So right click it and submit, and let's run it. And it should be finishing very quickly. Okay, completed. And now we can visualize the results. Right click it, results, and here. So this is the beam. And we can go results here and step and frame. See? And this is our natural frequency, because we only specify and we only instructed the system to give us the natural frequency between 1 and to 1000. So this is the unit is cycle and per second. And be very careful. Okay, so the natural frequencies unit here is cycle per second. So this one, cycle per second. So this one can be converted to the radius per second. 767.35 cycles per second equals 4821.4 radian per second. and you can do that. You can calculate that one. So you can see this is model 1, right? So you can see so this animation. Then I'm going to we're going to save it, and then I'm going to show you. This is a natural frequency. Natural frequency means that you don't need to apply any external load, and natural frequency is totally dependent upon the component itself. Density is very, very important. And for our second model, I'm going to neglect the mass of the shaft. Right? Neglect the mass of shaft. And these two models are very, very similar. So I'm going to copy this created model here and right-click it and copy model. And so this is one I will call is a shaft load, shaft with load, shaft with load. And then delete the copy. Then I click OK now. So this is a model. So the difference between these two models is that the shaft with load, and we are going to neglect material property density for here. And so this is the density. We are going to delete this density here. And delete the density, and then click OK. Now this is no density, and then we look at so we neglect the mass of the shaft, no density, no density, but the geometry we have loads here. So everything else, the step. I'm sorry, the step is different. Let me go. I'm going to this one. Delete this step. I'm going to delete it, and then I'm going to create a new step. So now this time the step will be a static general, and this is step 1. So this for the natural frequency that's different. For natural frequency is we use linear perturbation, but for this one we use general static general the step 1. Then we click OK now. So you can just put this one on and save it. So geometry, nonlinear geometry on and off, and should not give you different results because the load we apply here is very small. Right? So we change these load steps there. The boundary conditions and should be the same, but now we need to apply the load. We apply the load on load 1, the concentrated force, and so continue. Select point for the load and for this one. Just 1 second. Yes. This is one, this one. Yes, here. Select this one. Done. And the direction is negative y direction. Negative y direction, and we apply 18 pounds. So negative AT. Okay. And then load 2. Also concentrated force, continue. It's applied here. Done. And also the concentrated force in the negative y direction. So here is negative and 32 pounds. And click OK. Now we have applied the loads here. We have applied the loads here. And now then we can calculate the displacement, right? Any questions so far? Oh, no question. We are going to let's look at the mesh and what kind of mesh we have now. For this case, so make sure to use the manager here. Yes, so these boundary conditions must be zero. Boundary conditions must be started from the initial step. And the loads, these loads, non-zero loads from the step 1. Let's look at the mesh, the query here, and we can look at see if we have mesh here or not. Okay, we have mesh already. This is a mesh, and we have. And remember to save. So this is the shaft and dash with load. Now we have finished everything here, and then we create a job, and now this time from shaft with load, continue. So the job name we say shaft load. Shaft with load. Continue. And then now we can submit it. Okay, and we have finished it. Okay, so now and we look at the displacement, and we can right-click it and results. Let's see the view. Give you the view here. View bar, viewpoint. Viewpoint we put it here. A view, toolbar, views. So there we go. I want to have this one. Then we look at this, okay, and XY. I want to see XY. So this is XY. Let's see. Let's go here, assembly. So this is XY, okay, XY, remember, this is XY, this is left end, this is right end. Let's then go back to the results here. Results. So this is right, and this is left, and then we can deformation scale factor. Now we want to see, because this is a beam, and we want to see Okay, an OTB display option. So render beam profile. You want to see that? Okay, render beam profile. As you can see the profile here, and so you can enlarge it. And this is Vomisis stress. If you don't want to see it, and you can just go here, ODB displacement option, and toggle this off. So this is a line here, right? So this is a beam, and then we show the displacement in the y direction. Go here, U, displacement in the y direction. Now, I'm going to show you on how to get the displacement and tool here. And we know the query, and we know the load. This one, so remember, this case, the position is base coordinate -1.15. So this is -1.15. Where we apply this is a load, it is 2, and from this is from this end, from here. It's 1.15 and plus 2, and gives us 0.85, right? 0.85. We need to find the displacement at 0.85. Let's see. Where is the 0.85? .85. So the very left is 11.5 coordinates. 11.5. So this 11.5 coordinates. And then 11.5 and then plus 2 equals 9.5. You can just move and to go to 9.5 minus 9.5. Minus 9.5. Here. Just 1 second, let me see. Here. So here, you remember here, the left end, very left end is 11.5. 11.5 here. No, we don't. deform. It's 11.5. 11.5. Then we go to the in the positive x direction for 2" we have 9.5. Go to minus 9.5. We see minus 9.5, minus 9.5, minus 9.5, minus 9.5. Here we go. Minus 9.5. Here, and record this number, 9.5. We cannot go exactly, but you can just record it. Okay, 9.51. You can record this number. So that is or 9.48. Well, I cannot go exactly 9.5 there. Okay, you can just select one point that is close to the minus 9.5 to record the U2, right? If we use 9.5, don't go exactly 9.5. Jeez. We just cross it. Okay, you can just get this at a negative 9.5, the value, and record it. Or 9.51, okay, 9.51 or 9.49. That'll be good enough. So this is your displacement. And then the same thing from here, and you can just you can just come here and to see what is what is the position for the right end. The right end is on 4.49. On 4.49, and then 4.49. That is this is 14 and 16. So the location where we apply 32.4 and the center of this is the red baron system is 2. And so this is 4.49. And then we go to the left for 2 inches will be 2.49. So here, go to the 2.49. Okay, here, original coordinates. 2.49, I saw it. to 2.49, the U2 equals minus 1.14176 E05. So that is the U2 displacement of this system. And please remember, so this U1 and U2 is the displacement at these two locations when you apply on both loads. And also, when I give you the example and to illustrate on how to use relay method, the delta A and delta B should be the displacement that when you apply both deflections, right? So this is a deflection at the 18 pound force and the deflection at 32 the pound force, and you get now is the delta A and delta B used for relay method. However, for the Darkley method, and I told you guys for Darkley method, and we use delta AA and delta BB. Delta AA, okay, I just suppose, and for the point where we apply the 18 pound force, and we call point A. And for the point where we apply 32 pound force, and we call point B, okay? Delta AA means that the deflection at the point A, and because the force and you apply it at point A. And delta BB means the deflection of point B because of the load you apply at the point B. So if this is the case, delta A and delta B, delta AA and delta BB should be get differently. Now, so up to now, and this is delta A and delta B, and they are the deflection for A and B when both, this is a load, both loads are applied at the point A and the point B. So this can be used for, this is a relay method. For the Darkley method, what you can do is this, okay? For Darkley method, suppose now I want to get, let me see. And so I can just create another one. So another copy. Put another copy model. Now this time I will say for Darkley method, Darkley method D. Right? So Darkley method means Darkley method D. Darkley method D, what's the difference for Darkley method D? That means you only, at one time, you only apply one load. Now, in order to get the delta AA, right? I only apply load A, load 1 here. And so I just surprise it. I just surprise the load 2. I only have this load A now, right? And then I create a job. Double click it and the job for this one, and it's from shaft with load Darkley. So I will say Darkley for DELTA, Darkley AA. Darkley AA means that delta AA means that I only apply the load at the point A and then to get this deflection at the point A. So continue. Click OK now. Now I can run it now. For this one, I only have one load. I submit it. Now it's completed now. Go here, right click it and visualize, and I use this one, X, Y, right? So, and then I can check I can probe the displacement in the two direction. Go here, tool, query, and then probe value, and the nodes here, and this is, I don't want to see the vertices. I need to go here to change. Here I use U2, okay, and then I go back query and probe, and make sure these nodes here, so this U2 will be displayed. And I just pan it a little bit, enlarge and enlarge. Now I want to see it. So I know here the very end. I need to look this one, 11 negative 11.1. This is what we just got, right? So the coordinates of this left end, and then we know that the location where we apply 18-pound force is 2 inches to the right of this left end. So we go 2 inches right. Negative 11.4 plus 2 equals 9.5. 9.5 here. Go to 9.5. 9.5. This is what we just did. 9.5. 9.5. 9.5. There is no 9.5, and you can just use 9.51 or this 9.48. It's okay. Just be consistent. Use this one. Value is very close, right? And you can just use this value, and U2 equals negative 5.94657 E negative 0.6. And that one is your delta AA. And you need to record this one. And then I click cancel here. Now, how can I get this is the delta BB. Delta BB means that I only apply load B and without load A. Now I can just resume this load 2 here, resume. But I want to suppress this is and this is a load 1. I suppress it. And so here you can see I only have this load. So now I save it. Now I create another job. Another job we call also darkly and delta. Now this time delta BB and click continue. Done. And then I run it. Submit it. Oh, it's completed now. We can visualize the results. Results here, and we use this XY, and we enlarge it, and we pan it a little bit. Now remember, this time we are going to focus on the displacement at the point B, and because of load B. Now we know that, and we do this same thing. Results here and field, and we select this displacement. And in the second direction, in the Y direction, click OK now, and then we click Tools, Query, and in order to get this query and probe value, and here, so for the very right end, it is 4.49 coordinates, right? And then we move on 2 inches to the right. Two inches to the right, and 4.49 to the right, to the left. I'm sorry, to the left will be 2.49. Yeah, 2.49 U2 equals negative 8.37551 E0 Z negative 0.6. That is your delta BB. After you get delta AA and delta BB, and you can get you can use the relay method to get the results. Any questions so far? Okay, I'm going to end today's the tutorial video, and I will post it very quickly, so you will have access to these results.